Yeah, Kewen will tell us about this SIS infinity and more.
Okay. Thanks everyone for coming. And I was trying to follow Peter's way of presentation, like doing 1 hour of introduction with slides, and then the second hour will be on board. But I couldn't stop myself making slides, so it will be 2 hours of. How can you stop picking your slides?
Sometimes I've already made before versus.
Okay.
Just get really lazy. That's what I do.
But yeah, that's also for me. But when I started, I couldn't stop myself. Okay, so yeah, this is about no exponential quantum speedup for this problem called short integer solution problem under L infinite norm, which I will explain later. And this is a joint work with Robin Kossary from Google and Ryan O'Donnell at CMU. And this part of the work was done while I was doing internship at Google. Okay. So the outline of the talk will be like this. I will start with some toy example called F3 vector subset sum. And I will explain the problem, tell you about our result and prior works. And then I will say some like general motivation of this problem. And this will be the introducing example. And then I will proceed to the main problem, which is on the title, the short integer solution problem. And I will emphasize more on the crypto motivation behind this problem. And then we will see a full generalization that captures like this subset sum and also this SIS infinite problem, which we call like SIS problem. And for this problem, I will say more about the quantum connection about it. And then I will go to the proofs, like the algorithms. Okay. So let me begin with this toy example. The problem is pretty simple. You are given vectors in over the field of 3 elements, and the vector dimension is n. And then your goal is to design an algorithm to efficiently find a non-empty subset of those vectors that is sum to the 0 vector and the modulo 3. And this is called F3n subset sum. So formally, the input will be V1, V2 up to Vm, which are m vectors, and each one have dimension n. And the output will either be a subset S, which is non-empty, or a bot, like you didn't find a solution. So the condition is when you output the set S, you need to ensure that when you sum over the vectors in S, you get 0 vector. And if you output bot, then it means you cannot find such a subset S. And crucially, this is a subset sum, meaning that if you view it as a linear dependence, then you only allow coefficients that being 0 or 1. You do not allow 2, which exist in the field of F3. That's why it's non-trivial. Okay, so here is an example. Like, assume we have 6 vectors, and each vector has dimension 4. And these are like those vectors. And if you try to run your algorithm, you may find, well, here is one solution. Like you select the second, the fourth, and the fifth, and you add up all the rows, you get 0 modulo 3. On the other hand, there may be like more solutions. Like here is another solution. You can select the third, the fourth, and the last one. And if you check all the rows, it still sums to 0 modulo 3. So there may be multiple solutions, and you just need to output one of it. Okay. Oh, by the way, feel free to ask me any question. So this is the general problem, and we can plot its difficulty based on n, the number of vectors you get. So let's think of n as some fixed parameter that goes to n, which is a dimension, and think of the problem being parameterized by the number of vectors you receive. And here is the hardness landscape. So when you have fewer vectors, then the problem will be harder. And when you have more and more vectors, then the problem becomes easier. This is because you can always throw away vectors and you don't use it. That's okay. So when the number of vectors is n, this problem is NP-hard, meaning that even deciding whether there exists a solution or not, it will be NP-hard. Okay. And then when m is 2n, you will be guaranteed with a solution. Like you should never output bots when you have more solutions, when you have more vectors than 2n. And this is the total search problem, or you can like in complexity word is the TFMT problem. And in fact, this will be the threshold that we care about. Like we will be working on the regime where the solution is guaranteed, and we want to find one. Okay, and then between n and 2n, there is a middle area, roughly n plus some poly of n, but this poly is smaller than 1. So for example, n plus root n or n plus n to the 0.01. And in this regime, it's really like this learning with error territory. Like you will have some crypto assumptions and you base on those assumptions to design protocols. And in particular for n plus root n, this special choice of parameter, there is a famous algorithm called Aurora-Gur algorithm that solves learning parity with noise. Okay, I will say more about this later. And then here is a quantum part. So when do you have efficient algorithm? So the first result was about quantum polynomial time algorithm by Chen, Liu, and Zhandry. They show that if you have quadratic many vectors in terms of the dimension, then you can use quantum algorithm to produce a solution S with high probability. And it turns out this constant C, although they didn't compute, but it's a half. I'm hiding low order terms here, like just focusing on the leading term. However, this algorithm, like this problem and the algorithm was actually implicitly studied in prior work. And this is work by Ivanians, Sansema, and Sansa. And this paper actually appeared before this quantum paper. And they showed a classical polynomial time algorithm exists when the number of vectors is n squared over 2. Okay. And our work on this problem is to improve this a half, this constant, to 1/3. And I will present this algorithm. It's not too complicated, and it will give a lot of interesting problems, open problems. And the main open problem at this point is to close the gap, like between this 2n and this n squared over 3, roughly like linear in n and quadratic in n. What happens in the middle? Like, can you improve the lower bound or design better algorithm?
So do you know at 2n there's no polytime algorithm?
Yeah, like the proof is existent. Like they convert the problem into a polynomial. And whenever this polynomial outputs non-zero value, it will correspond to a solution set that. And then they use a polynomial method like the degree, like the maximal monomial is having non-zero coefficient, and that's why it's not a zero polynomial, which means it always has a some non-zero value. And that's why that's how they prove this 2n degree threshold.
I was asking, is it known that there's no polytime algorithm at 2n?
But no reasonable hypotheses.
I don't think there is any conjecture regarding that.
Oh, sorry, I don't understand this polynomial method part. I thought the existence of solution should just follow from the pigeonhole principle.
Oh, if you do pigeonhole principle, I guess it's like U1 subset. It's not like 0, 1, plus 1, or like minus 1. I think if you do pigeonhole principle in the most direct way, you will get minus 1s.
I see.
Like you have two subsets that are equal. So if you want to produce 0, then you use 1 minus another one, and that's plus minus 1.
Yeah.
Yeah.
How does the picture change when the field is a power of 2?
Oh, yeah, so if the field is a power of 2, then you can view the vectors like, well, like let's say the field is 2 to the k. And then you can view this field 2 to the k as a vector of length k of binary field. Because we're talking about linear algebra, so we can ignore the field structure, like the multiplication structure. We just consider the additive group. And then you can think of this as like longer vectors still over F2. So that is like for fields with the same characteristic. But for different characteristic, this is actually getting into the picture of like SIS infinite. Like it's a different problem. Like here is F3.
So for like for FP to the n, like the total search thing would kick in for P minus 1 times n?
Yes.
Just making sure I understand the
Yes.
problem method thing. Okay.
Yes, P minus 1 times n plus 1.
Plus 1, okay.
Yeah,
Is there?
this is actually sharp. So,
Okay.
well, I should say here,
So the plus 1 there too?
so for F3 to the n, if you consider this are your inputs, so E1, E1, E2, E2, up to En. So these are your inputs. There are 2n vectors, and EI is the basis vector. And then you can see, like, if this is your input, then no matter how you choose your subset, you cannot produce an all-zero string. This is because every entry appears twice. So this is like m equals 2n, and there is no solution. And when you add one more vector, there will be guaranteed solution. So that is actually a sharp thing. Yeah. Okay. Any other question? Okay. So let me say about like the general motivation of this problem and like this work. So why do we study this F3 subset sum? Well, this is actually a natural problem with many different perspectives, and I hope this is more like an invitation. Like I give a few examples and in different views, and then maybe you have this like domain knowledge, and you can come and improve the algorithm. Okay, so from complexity theory, this is like subset sum is a complexity theoretic problem, and also it's talking about satisfying linear equations. So this is also a link set. So if you want to prove hardness, maybe this is where you can use your tool. And also in terms of discrepancy theory, you can view this problem as a vector balancing problem. So you have a subset of item, and you want to assign like 0 and 1 values to the item so that you balance the weight of every set. So this is the study of the vector balancing problem, and it's from discrepancy theory. And also this has natural coding theoretic interpretation between like the generating matrix and parity checking matrix. And it has a name called ternary syndrome decoding with maximal weight in some literature. So maybe there are some coding theoretic tools can be applied here. And lastly, I want to emphasize this connection to crypto, as I already mentioned. This is related to learning with error problem. Although here we are working on the field of 3 elements, and the arrow is like binary arrow. So these are different names or perspectives you can take on this problem. Yeah. And also, this problem has been used as hardness assumption in concrete crypto schemes, and they assume it to be post-quantum secure.
This they plant the solution in this example.
So one of them, they planted the solution, and the other one, I think they don't. I will give out the parameters later. So there are 2 signature scheme. One is called wave, and the second one is crystals dilithium. And they use this kind of problem as a hardness. In some parameter regime, they assume it's hard. And then, of course, there is quantum advantage. We want to identify problems, like interesting problems, where quantum computer can outperform classical computer. And This is also one of the motivation. And also for this problem specifically, it's like a warm-up problem for the main problem. Okay. So what is this main problem? It's short integer solution under L infinite norm. So the problem setup is similar to before. We have a bunch of vectors, although here we work on a general prime field, P, and we want to output a zero vector. So we want to do some linear combination so that we output zero vector. And the constraint here is we have an additional input H that controls the weight of each coefficient we can use. And we need to make sure every coefficient, the absolute value, is at most H. Okay, so even though this is like a prime field where like you go from 0, 1, 2 up to P minus 1, and then you roll back to 0, but you can still view it as like integer numbers and take the absolute value. Okay.
So here, if like H is 1, you do allow minuses.
Yes, yes. In this, like, this is more like a symmetrized problem. Yes. So for H equals 1, I do allow minus 1. Yes.
For larger P than 3.
Yeah, for P larger than 3, it will be non-trivial. Yeah. Okay, so why is it called short integer solution? Well, the first part is short integer and the second part is a solution. So that's why it's called short integer solution. And why it's L infinite norm is because we impose entry-wise constraints. So it's like L infinite norm is small. Okay.
You think of like
the coefficient
of
vector.
CI is
Yes.
to be bounded in L infinity.
Yes, yes. There are versions, actually more standard versions, where you talk about L2 norm, and that's used in crypto reductions, like worst case to average case reductions of lattice problem. But we care about the L infinite setting. Okay, so here is an example. So assume the prime P is 101, and then you are given m vectors of like dimension n, and every entry is in field 101, and you want to find the linear dependence among them, where you only use coefficients that are at most 5 in absolute value. So this is one instantiation of the problem. Given this problem setup, let me make a few remarks. The first one is for small p, like for p equals 2 or 3, this problem is trivial. Because if you allow 1 and minus 1, this is where you like this is weight. Then for prime being 3 or 2, this is allow everything. Right. So we will just look at primes that are larger than 3. And the second thing is if H is large. For example, if H is larger than P over 2, then this problem is again trivial. This is because you only have P elements in your field, and if you like view them as minus P over 2 up to P over 2, then once the weight is larger than that, you allow everything. Okay. So the smaller weight constraint will be oh yes.
Is it important that P is a prime here? Like you can model composite numbers?
Yeah, so for simplicity, I'm just assuming P is prime, but our algorithm and a few algorithms in prior works also work for like modulo composite numbers. Yes. Yeah, there is actually a reduction, kind of like Chinese remainder theorem. Yeah.
No, but I don't understand, like if the field is a P power, it still has
if the
something. Yeah.
okay, so if the
You
field
have characteristic which is like it reduces to some higher power of the base field FP, right?
so are you talking about composite number or
No, I'm asking about
field?
the CIs. Like the CIs still when they get over P,
Yes.
like they round back. And
Yeah.
P, like even if you're over a power, like a power base field, like FP to the T for some T.
Oh, then
And
this
still characteristic is P.
yeah, so the coefficient will be like still within this 0 to P p-1, not in this bigger field, because then
That's
how do you?
I think
So doesn't it just reduces to
No.
FP to the TN?
Right, so
Yeah.
when he was
Yeah.
asking about
Yeah.
opposite
Yeah.
numbers, he was
Yeah, okay, so it's like, it's not more general.
Yeah, so this
This is general enough.
I think he meant like
He meant
non-prime
like,
power.
it's not a field.
Yeah, you can do this.
So it's not.
Okay, you didn't assume a field as a base, like you assume.
Yeah,
Just,
you can do this.
yeah, that's what's clear.
Okay.
But now, like, the question was about Z mod M for.
Yeah, that you can also do similar stuff, like Chinese remainder theorem style thing. Yes.
I suppose this will also work for any abelian group then. Or you just like decompose it into.
Okay, so if you talk about abelian group, then what will be the like a weight constraint?
Okay, I see.
It has to have some number in it. Yeah, so I think our algorithm can be generalized in certain ways, but the problem setting might need change. Okay, so more question? Okay, so for this problem, if you have like smaller h, then the problem will be harder. And for example, for h equals 1, this means you allow coefficients that are -1, 0, and +1. And this is, you can view this as a problem to look for collisions in linear hash. And here is how, like how you view it. So you can like stack all the vectors into a matrix called V. Here, the matrix will have n rows and m columns. So each column will be a vector here. And you view it as a linear hash function that you take a message x of binary of length n, and you compute the v of x, which should be shorter, like n should be smaller than m. And then if you want to find a collision, meaning that you want to find x and x prime in the message, and they have the same image, then you can subtract it. So it's equivalent to find this x minus x prime vector, which will have coefficients -1 and 0 and 1. And you can go backwards. Like once you have such solutions, you can roll back and to provide x and x prime. Okay. So as Ryan asked, in this general setting, like for larger prime, the solution, yeah.
And it's conjectured that you cannot find linear hash.
So for that, I actually don't know. I think they conjecture something that's even stronger, because if you use this linear hash, it's not very efficient because it will be a dense matrix V. And I think they, in some like ring LWE setting, they assume this matrix has some cyclic shift pattern that they can even boost the computation. So they even assume the hardness of that. So I think people should, I guess in general, assume this problem is a hard problem that you cannot find collisions, but better to check with those crypto people as well. Yeah. Okay. So yeah, so the solution will be guaranteed. So in this problem setting, you can also say, oh, what if there is no solution? I should output bot, but this will not be the typical setting that we care about. And why do we not care about it? Because if you think P is a constant, then once you have like more than some amount, which is linear number of given vectors, you can always guarantee a solution. And the proof of this is also using this polynomial method. And it is sharp, like this p-1 is going to have similar pattern, like we repeat every base vector like p-1 times. Okay, so these are the remarks. And now let me talk about like crypto motivation behind this problem.
Why can't we use the pigeonhole principle now? Because we have -1.
I think if you use pigeonhole principles, then
But the field is larger, you will get other.
yeah. Yeah, yes, you do. You could get some one, but I think it's not as sharp as this one.
Gotcha.
Okay, so let me talk about the crypto motivation of this problem. In our setting, we will focus on the number of vectors being much larger than the number of like the dimension, and there will be many solutions guaranteed. And we just want to find one solution. And in particular, our focus will be on the number of vectors being at least quadratic of them. Okay. And in the crypto setting, especially in the learning with error setting, the number of vectors you have will be like very close to n. So it's n plus n to the 1 over c, where c is a large constant. And here, a solution may not be guaranteed to exist, but you will plant one. And the problem is to distinguish of the two scenarios where you don't plant one or you plant one. And you can also say we want to find such planted unique solution. Yes.
What does learning with error mean?
So it's like you are given linear equations, but every value is perturbed a little bit. And then you want to find the original solution. So if I give you a linear equation system, you can use Gaussian elimination to find the solution. This is pretty efficient. And the way to make it less efficient is to add noise. So you are not sure whether the linear equations you get are accurate or not. I think, yeah. And this is learning with error problem. Okay. So, and back to this concrete signature scheme, what the parameter setting there is like the dimension n is around 1,000, and the number of vectors will be around 2,000, and the prime is 2 to the 23, and the weight constraint is roughly p over 8. And they assume the input vectors are random. And if this problem set, like if this set of parameters is hard, then they are secure. And in general, the ratio between these parameters is m is roughly 1.9n, and p is a prime that's much larger than n, and then h is still set roughly p over 8. And they assume random average case input. So, how should we think of this like security? Although this is not the focus of our paper, but let me just mention in case people are interested. You can run through the literature of worst case to average case reductions over lattice problems, and these are works by Atai, Misiasio, and Oded Regev. And they, if you run through their reductions, you can kind of see this parameter regime will be hard, assuming some worst case lattice problem are hard. So here, the number of vectors will be roughly n log n, and the prime will be roughly quadratic and so on. And then the weight is constant, and you assume you have average case input. So in my opinion, this H is really like the key difference between these two settings. Like here, this is a more relaxed version, like you can even allow the weight to grow with n. And here is really a constant. Yes.
Scheme is also in the planted setting.
You mean our result?
No, the scheme that you have
Yeah,
described.
there is an iTimeWalk crypto system based on the same.
Okay.
Yeah. Okay, so this is like the complexity theoretic result of in terms of hardness, and this is what they actually use. Okay. And we do not break them. Okay, our algorithm do not break them. Okay, so let me talk about the results, and you can compare with those settings. So this result by Chen and Zhandry from 2021, they assume k is a constant, that is an odd number, and assume you have like roughly n to the k many input vectors. So m is the number of input vectors, and their algorithm is quantum and polynomial time in terms of the input. And the largest H they could run on this number of inputs is P minus K over 2. So recall.
The smallest H there.
Yes, the smallest H they can run their algorithm for is this H.
So you have almost all coefficients.
Yeah. Yes. So recall that P over 2 is like everything, and then they subtract like K from the, yes. They have almost everything.
They delete the constant amount of coefficients.
Yeah.
Are able to solve it.
Yes, like what, like for every coefficient you want to remove, they need to pay an extra n factor in terms of the number of vectors you get. Yes.
Is there like an obvious reason why K being odd is important?
Oh, it's just like a, here, you need to divide two. Yeah, you need to divide. Yeah.
Okay, I have a question. P over 2 is trivial, like deleting one coefficient, is it immediate that you can?
It's not that immediate because if you think of field being 3, then deleting 1 is like subset sum.
Sure, I mean, wait, if the field is 3,
Yes, so you have 0, like -1, 0, and 1. If you can delete 1, then
right?
that's
and
like
in the
subset sum.
symmetric, okay, I meant like delete 2, right? Like in the symmetric version.
Okay, in the symmetric version, I think you can do something clever when field is really large and you assume the random input. You can just run your Gaussian elimination and hope the coefficient doesn't appear. Yes, that, like for example, P is way larger than N.
Sure. Okay. Clever is maybe an overstatement for like just running things and hoping it won't.
Okay.
But, okay, I see. Like,
Yeah.
sure, for P large, I agree. But no, I mean, we're saying, okay, it's just removing a constant number of.
Okay, let's say P is 7 and you want to remove 1.
Right.
We don't know how to do it in less than n squared number of vectors. Yes. Yeah.
What's going on with the slash GG there? Because like if K is 1 and we're looking at 3, then you're just saying if n is greater than n, you have an algorithm for the F3 problem. So
Oh.
like, how much bigger is m than this P to the 4 times K?
Oh, you're saying K equals 1.
Yeah, when K is 1, right, you want to be much bigger than.
Oh, if K equals 1, then, okay. So in the previous slide, I said H will be, like the problem will be trivial if H is like P over 2, but there is a flaw. So if K equals 1, this P minus 1 over 2 is the flaw of P over 2.
No.
So it means,
The trivial.
so it means the trivial setting. So, okay.
Oh, sorry, yeah, because you allow -1.
Yeah.
Okay.
So
He actually removes K minus 1 coefficients.
yeah, so this is the trivial.
Yeah.
So and that's consistent because you need n vectors to produce linear dependence.
Yeah.
You have
Also, one is important that you restrict coefficients less than h instead of like arbitrary 2h plus 1 coefficients.
oh, that actually is a full generalization.
Oh,
Okay, you need to wait maybe like 5 slides more.
okay.
Okay, so this is their work, and there is a work by Imran and Ivanias, and they were not aware of this problem, but hidden in their paper, you can turn their algorithm in, to solve this SIS infinite problem, and this is a parameter they get. So they need to assume K is a power of 2, and then the number of vectors you get is also n to the K, but the dependence on P will be worse. And it is a classical algorithm. And the H they can get will be P over 2K. So here is minus K, and that is dividing K. So that is way better. If you think of K as like 4 or 5, then that is P over 10, and here is P minus 5 over 2. Yeah, but they do have worse dependence on P. So, so our work is kind of like achieving the best of two worlds. We build on the techniques in that paper and improved them and generalize them in different settings. And here is our results. So assume k is a constant, then if you have n to the k vectors, now there is no dependence on p. And we have a classical polynomial time algorithm, and h, the smallest h we could allow is p over 2k. Yes.
Is there any reason why h being proportional to p over k should be the right dependency when n is around n to the k, or is this just what you happen to get?
Yes, this is what we can get based on our algorithmic.
Do you have a guess for what the right trade-off should be?
Well, I think there should be dependence on h. Like you cannot just get like n square vectors could give you like subset sum.
Yeah.
I don't think this is true for large prime. But what is actual dependence between them is unclear to me. Yeah. Okay, so some remark, because we shaved the dependence on p from both like this Chen-Zhandry work and that work, our algorithm actually runs in time polynomial in n and log p. So we could allow like exponential large prime fields. So that's okay. Although this two will not be okay. This is just a remark. And our result is in worst case. You can have worst case input. And it's deterministic. Okay. So this is a slide about further generalization that Henning asked. So so you could ask, okay, why do we like enforce this coefficient being centered around 0? Why not arbitrary? And yes, we can do that. So the problem in general is still asking for linear dependence. Okay, and the constraint will be you give me a set of allowed coefficients, and I need every coefficient to be allowed in this linear dependence. And here is an example. If you center it around 0 from minus h to h, you get the SIS infinite problem. And if you set a to be 0, 1, this captures the subset sum problem. And if it's minus 1, 0, and 1, you get this Clichy finding problem. And it's more generally. And also, because this A is said to be arbitrary, and if you remove 0 from it, like you don't allow 0 as your coefficient, then this may not always have a solution. Because you can set all the vectors except 1 to be 0 and this last one to be non-zero. Then no matter how you linear combine them, because you don't allow 0, then this won't have a solution. So in this setting, for simplicity, let's assume like the input vectors are random. So this happens in very rare probability. Yeah, some of our algorithms still works in worst case, but just for the presentation simplicity, let's assume it's random. Okay. So for this problem, the work by Chen and Zhandry showed that you can remove k elements using the like n to the k vectors. So this is the same p to the 4 and n to the k. And then the largest or the smallest allowed set will be of size p minus k plus 1.
As before.
As before, yes, as before, yes. As a sanity check, if k is 1, then this is like linear. And here A is everything. So it means you will witness a linear dependence if you have n vectors, which is consistent. And if you set k equals p, like why do we assume k is less than p? This is because if you set k equals p, then the size A will be 1, meaning that this problem is not interesting. Like you just plug in the coefficients and you check. This is not interesting problem. Okay. So for our results, we will stick to the same condition that they can get. Like what is the cost to remove k elements from the field? So our algorithm is a classical algorithm, and we improve the dependence of p into log p. And if P is really large, it's larger than like 4 to the k minus 1, then the number of vectors you need is actually n squared. So this is actually the typical setting where k is a small constant because you want a polynomial time algorithm, and P is really large in many of the crypto application. So this is a scenario, and we could improve this n to the k into n squared. And if you remove this assumption and assume P is a prime at least 7 and k is at least 3, then we still save something. Like they have n to the k and we have n to the k minus 1. And in our analysis, you can actually save more if you do this case analysis further. Like you can save like maybe -2, -3, even linear in k, but that will make the table bigger and messier. So I'm not doing this. The whole message here is we can improve them.
But there is no P over K.
No.
It's very different than the symmetric.
Yeah, that's different, yes. And in general, like what if P is, like you really want to know what happens when P is 5 or P is 3 and when K is like 2, things like that. Then in general, for all the prime at least 3 and for all the k at least 2, we can match their n dependence. So, but still, like we improve their p dependence. Okay, there is no like asymptotic, like assume p is sufficiently large or something. And this is actually like important because we want to dequantize the quantum algorithm in all the parameter setting. Maybe they will say, oh, maybe like this setting, we still have a non-trivial thing that outperforms classical. And we want to study whether our techniques can also rule that out. So that's what we do. Okay, any question on this? Okay, cool. So this is a full dequantization. And why is this dequantization interesting? And this goes to the motivation of quantum. So about quantum speedup, in terms of quantum computing, we want to know whether quantum has advantage over classical, and we want to find explicit problems where quantum algorithm has exponential speedup over the classical ones. Maybe it's just a candidate, but we want to see something different. So, for example, there are proposals regarding simulation of quantum system. There are like hidden subgroup problem as instantiated of factoring or solving this discrete log problem. These are all like conditional speed up because we don't know whether that actually is in P or not, but they are still candidates. Like we are interested in these kind of candidates. So there are a line of works proposing candidates using different techniques. And this is called Regif's reduction, developed by Ode Regif, where he used it to study the worst case, average case reduction in lattice problems. And there are papers converting this harness reduction as an algorithmic tool to find candidate problems where quantum has an advantage. And in particular, this is like the key idea behind Chen and Zhandry, and also the work by Yamakawa and Zhandry. And more recently, it's the DQI team at Google by these people, and Shaluk and Tillich. And these problems are all captured by this full general ASIS problem. Like you should specify the prime, like the field size and what is the allowed set of coefficients, and your algorithmic purpose is to find linear dependence given those allowed coefficients. These can all be captured by this setting. Yes.
Can the dequantized Regif's reduction in function?
No, because we need. Well, this is actually like my next slide. Like the number of vectors we need is really large. It's like quadratic, at least quadratic, and we cannot break them or like dequantize those things. So it's an interesting thing, but still we don't break crypto assumptions or things like that. Okay, Yeah. Okay, let me say more about this quantum algorithm, like this reduction type quantum algorithm, and how you view it in terms of this classical problem. So these are the like three line of works. The first one is by Chen and Zhandry, and here you should think of the vectors as random input, average case input, and A is some arbitrary set. And then they assume P is a polynomial in N, and the number of allowed coefficients will be near P. So it's P minus K plus 1. And then the number of vectors they can, when does their algorithm kicks in is when the number of vectors is sort of roughly n to the k. So for Yamakawa-Zhandry, the VIs, the vectors will be the vectors defining the code called folded Reed-Solomon code. I'm not going to into detail of this, but it's a structured set of vectors. And they also assume A is random, and the field will be exponential in N, and the size of A will be P over 2. So you will have a random set of half the coefficients allowed. And the number of vectors you get will be roughly 6n. And this is because you use this folded Reed-Solomon code, and that's the trade-off you get. And for this DQI work, they work on Reed-Solomon code. It's not folded Reed-Solomon. And A is also random. There are many settings, but I'm just picking out one setting to explain things. So for random A, that has half of the coefficients, and P is linear in N. So the field size is linear in N. And the number of vectors you get is 4n. It's also linear in N. And this is where they have quantum advantage proposal, like they have quantum algorithms kicking.
So all of the settings have good quantum algorithms.
Yes.
I remember Yamakawa-Zhandry was some kind of quantum advantage in random oracle model.
Yes. Yes. So in the random oracle model, they can actually prove like the security, like the advantage. And in the non-oracular setting, you need to instantiate those random oracle, and maybe your guess will be plugging in some concrete instantiation of the random oracle, like use some hash function. And this will be non-oracular setting of the Yamakawa-Zhandry problem. And we also don't know how to solve it. And there is no oracle. So it's a candidate quantum advantage. It's not provable quantum advantage. Provable quantum advantage only exists in the query model for Yamakawa-Zhandry. Okay, so that actually leads to the classification of these three. So as I showed you, this Chen and Zhandry work is no longer quantum. It's actually classically easy because of our results. And as I mentioned, this Yamakawa-Zhandry problem is different because you can prove advantage in the query model, and you instantiate the query oracle by some crypto hash function you like, and you can try to break it.
Sorry, what is the query model?
So you assume this A is random, and you don't know where it is random. You need to ask, like, is, for example, 1 allowed, is 5 allowed, and every time you query, and this is called query model. And in this setting, the number of query you need to make if you are quantum algorithm is much, much, much smaller than classical algorithm. So this is how they prove their security. And for DQI problem, it still seems classically hard. Like our algorithm doesn't break them. And the key question is why? Like these are all based on Regev type reduction, and the setting seems to be all captured by this ASIS problem, and we can give some interesting algorithm for them. And why do we not dequantize them? Right? So the observation is we can handle worst case vectors. Like most of our algorithm works in the worst case. So having some strange folded Reed-Solomon code vectors, like Reed-Solomon code vectors is not a problem for us. And we can also handle like exponential large prime. So the field size is also not a problem for us. And A is large, which is actually beneficial for us. So our algorithm works for these choices, but we need a lot of vectors.
You need a lot of vectors and you need large, it's very large.
Yes.
There's a big difference between
Yes,
P over 2 and P minus.
Yes, yes. So we are like roughly like in this territory, like n to the k. And here it's like linear. And we have no idea how to even like get n squared. So this is a key difference. So our trade-off works for any of those like worst case instance, exponential p and a of large size, but the trade-off will produce you like the m needs to be way larger than linear. Yes.
Okay, so if m is much larger than n squared, but you still have exponential large p, and in the Kewen model, can you solve this lemma Zhandry?
Okay, so that is actually like not the right question to ask because when you fix VI to be like to define the folded Reed-Solomon code, it actually fix M to be that. Like you can't say I have larger M. Like this is defined by the piece, like by the code you choose.
Oh, but I guess p being exponential and you only have query access to A, it's like this doesn't like your algorithm still works when you only have oracle access to A. Is that right? You just need a lot of vectors and
we need to look at the structure of A. Like we need some structure about A. So if you have a black box query access to A, yeah, I don't think our algorithm also works. We need to find some structure inside A, so that it works. But for some parameter regime, it will work.
I mean, in the middle, this is also my question. Like in the middle, p is already exponential in n, and m is like just linear in n. So, like, even the description is like too long to.
Yeah, that's the point. That's
Yeah.
why they get a query.
That's why this only makes sense in the query mode, right?
This makes sense in the query model, and that's why they get quantum advantage. But you can instantiate it using some real life hash function, and that could still work for p being exponentially large. But this real life instantiation, the hash function, may still will be an efficient algorithm. Like it won't be as complicated as a random oracle.
Yeah, but then the random oracle doesn't tell you anything.
Yes, and then that's the random oracle doesn't tell you anything.
So it's a concrete problem here. We have no reason to
Yeah.
think that it has a quantum advantage other than just believing.
Yes, or you can try to do some work to analyze the specific hash function you choose, but I think that
Then it's not as elegant problem as these are.
Yes.
So maybe another question. When you say still seems classically hard, so like, is this actually still a conjecture? Like, don't you believe that?
Oh, so for that setting, there is no oracle. Like they cannot prove like a hardness. They cannot prove hardness in their setting.
Oh, what I meant is, do you believe that it is still that it's supposed to be hard, or do you believe that maybe there isn't like another classical algorithm that will also solve that last?
I'm like half. I don't know. So this is a fairly new work, and there has been several papers posted in last 2 weeks about DQI as well. So yeah, we should wait and see. Yeah.
In the last 2 weeks? No. Okay.
like QIP deadlines and stock deadlines.
You probably remember the maybe decade-long struggle to find good assumptions for obfuscation. People propose things and then they were broke, and then propose other things and then they were broke. It was a long time. Yeah, so that's another proposal.
Yeah. I don't know whether that is actually possibly hard or easy. I don't know. At least our techniques doesn't work there. Okay, so the key difference is like the number of vectors we need is actually huge.
You're basically motivating understanding this problem ACs for other parameters than you.
Yeah, I'm just trying to connect the quantum side of this work to other problems. Yeah. Okay, so this is why we do not break them. And those are the background stuff, and maybe we can take a short break, and after that I will go into the algorithm, and it will also have 3 sections. Okay, maybe we can.
5 minutes.
Okay, so now I will go into the proofs, like share some algorithm details, and I will still follow the general outline. Like I will start with this F3 subset sum problem, and the key idea inside this will be like reducibility. I will define what is called reducible vectors, and it will be used as for later problems, the algorithm. And then I will proceed to this SIS problem and use reducibility and a new ingredient called weight reduction there. And finally, for the general SIS problem, there will be a general reduction, not weight reduction, a general reduction. And let's see how things goes. And if I don't finish, this slide is uploadable. That's the benefit of having slide talk. Okay, so this is the result or the setup. You have roughly n squared over 3 vectors over field of size 3, and you want to find a non-trivial subset that sums to 0. And instead of telling you this n squared over 3, like how do we achieve it, I will go from n squared and then add one idea of improvement to get n squared over 2, and then add another one to get n squared over 3. Okay. So let me begin with this n squared case, and the number of vectors you need is actually n plus 1 squared. Okay, so first we have this roughly n squared input vectors. We will divide them into n plus 1 batches, and each one has n plus 1 vectors. So like the batches on the top right, and the indices are inside the batch are on the top, the bottom right. And what we can do is we can compute linear dependence without like ignoring this 0-1 constraint. So we will compute the linear dependence inside each batch. So here I will use 1 and minus 1 and also 0 to denote the field of size 3. So this is the first batch. And importantly, it's not all 0 because I put n plus 1 vectors in it. And then I will partition them into 2 parts called U1 and V1, U1 and W1. U contains all the vectors I assigned plus 1 coefficient, and V and W are the vectors I assigned minus 1. And what does this mean is because they sum to 0, it means U equals W, right? And they are disjoint and they are subset sum. Okay, this is equivalent way of writing this linear dependence. So we will be able to compute 2 disjoint subset sums that are equal inside each batch. And as a side note, if any one of it is actually 0, then we are already done because it's a subset sum that sums to 0. So we assume they are actually non-zero. So this is
That's exactly the hash from before, the argument from the hash from before.
Yes. Yes. So, but also like for F3, like if you want to find collision, then it's trivial because +1 minus, it's only +1 minus 1, 0. So collision finding problem.
Yeah, no,
F3 is,
my remark is that this is the exact trick that you already discussed when we talked about the linear hash.
Yes, yes, yes. Okay, so we do this for every batch. This is efficient. So each batch I will produce some ui and wi. They are disjoint subset sums and they are equal. So what we can do is to do it again, like compute linear dependence again. But this time we will compute according to these u's. So this, for example, is our linear dependence beta 1 u1 plus beta 2 u2 and beta m plus 1 u m plus 1. And they sum to 0 modulo 3. And here, let's say the beta i's are 0, 1, and 2 for simplicity. I mean, that's 3 things. And depending on the beta I will do something different. If beta I equals 0, then beta I ui is actually 0. So I can just ignore it. If beta I is 1, then beta I ui is just ui, which I said is a subset sum inside the i's batch. If beta I equals 2, then it's twice of ui, but you can equivalently expand it as ui plus wi. And these are two disjoint subset sum in the i's batch and disjoint from all the other batches. What does this mean is, depending on the beta i's, we can substitute back all these subset sums into this linear dependence, and we get a subset sum equals 0. Okay, good.
Now you need to divide by 3 somehow.
Yes, well, divide 2 first.
Yeah, let's divide by 2.
Okay, now let's see like, well, this is actually like a very simple algorithm, and what is the trick to save half of the vectors? And this is called dimension reduction, and it's also simple. So if you recall what we did, we separated the first n plus 1 vectors and the rest of them. And of course, we'll partition the rest of them, but let's focus on the first batch. What we did is to compute some subset sum that equals to another subset sum that are disjoint. So we computed u equals w, where u is a subset sum disjoint from w. And crucially, 0 times u is a subset sum, 1 times u is a subset sum, and twice of u is also a subset sum. This is a crucial property we used. And I showed you how to use linear dependence to come up with this u and w. And then what we can do is to project or separate out the dimension of u from the rest of the vectors. So for every vj that is not the first n plus 1, we will write it as cj times u plus vj prime, where vj prime is in the complement space of u, and cj is some coefficients that is 0, 1, 2. Why can I do this? This is because I could handle the coefficients later using vectors from the first batch. So if you find a 0 sum in this complement space of u using the rest of the vectors, then when you compute it in the whole space, it will be an integer multiple of u, right? And the complement space is 0 out. And then this integer multiple can be canceled using the first batch. So this is like an inductive type algorithm. And the complement space is 1 dimension smaller. So the first one is n plus 1 vectors, we separate out. And the rest of the vectors, we will use it to solve the 0 sum problem in a dimension one smaller. And this will, like, combine them will be the total number of vectors. And if you do this, like, it will be n squared over 2. Okay. Okay, now let me say, like, how do you get n squared over 3? This is one extra trick. It's to explore the sparsity of how we come up with u and w. So recall that we use the first n plus 1 vectors to come up with this u and w such that any integer multiple of u is a subset sum in the first n plus 1 vectors. So this is where I define reducibility. So I say a vector u is reducible in this set T if any integer multiple of u is a subset sum of vectors in T. So in particular, what I showed you is a fact that reducible vector u exists if T is a size of n plus 1. And you can efficiently find it. And what I'm going to show you is reducible vector exists for T much smaller than n. It's 2/3 of n. One, you have like sufficient number of vectors, like n plus log n vectors. So this means you can separate out n plus log n vectors and then zoom in into a much smaller subset to construct this reduced vector. Okay, so with this claim, which I will show you, you can see how you get n squared over 3. So again, we have m vectors to begin with, and we will get a subset of it to construct a reducible u and project the rest of them into the complement space. And the key point is now we don't pick out n plus 1 of them. We just need to have 2/3 of them. And the rest will be used to handle like the complement space. And then if you do the calculation, it will be n squared over 2 times 2/3. This n squared over 2 comes from the saving of dimension reduction. And this 2/3 is because every time we only select out 2 things. And if you multiply them, it's 1/3.
So wait, let me just understand. Like the point is that if you take n plus log n vectors, you're actually guaranteed somehow to have two subset sums that are supported only on, which are the same but supported only on 2n over 3.
Yes, yes. Yes. Right. Yeah.
So like the size of T is not just to produce U, but also to produce 2U, right? So you
Yeah.
have all.
Yeah, so this will be efficient. Like you can efficiently construct that, yes. Okay.
But it's independent, like it's enough to take any n plus log n vectors.
Arbitrary. Yeah, this is worst case statement.
Is it sharp? Like, do you all need to?
I will talk about it. Yeah. Okay, so this is how you get to 1/3. And let me show you how to get that. This is a key claim. So as you already seen, the way we get reducible vector is to compute the linear dependence. So the equivalent way of writing that claim is to say linear dependence exists for a small set of vectors once you have a large set of vectors. Okay, why is that? Well, you can just go over the old proof. This is a linear dependence, and you separate u to be the ones with coefficient 1 and w to be the negative 1, and this will be your reducible vector. And then these are the subset sums, which means u is reducible. So this is how you go from the second claim to the first claim. Okay. Okay, now let me show you how to get linear dependence of smaller size. So we will partition m vectors into 2 parts. The first one will be like n vectors, and the last one will be k vectors, where k is log n. Okay, so v1 to vn and y1 to yk. What I'm going to do first is to simplify the problem. Let's do a basis change. Assume the first n vectors are linearly independent. Okay. And then you apply an invertible transform to make them like in the standard basis. You can do this conceptually. It's not necessary you have to do, but it will make the presentation simpler. And this linear transform will change this y1 to yk into some like z1 to zk. I don't care. Okay.
And now either the weight of each zi, one of the zi is smaller than 2/3, right?
Yeah.
Or
Well, not yet. Yeah. Well, so it's not guaranteed one of the zi will be small, but
no, I said just like there are 2 cases, right?
Yeah.
Either already the zi's are like sum of less than 2/3 of the ei's, or you need to argue something else, right? I'm just checking that I.
not like that. It's not like a win-win argument. It's like we do something about these and then we use these. So it's not like either Z is something or E or E is something. It's not like that. But it's simple, and so you can maybe see like our approach. So what we will do is we take a random linear combination of the Z's, and then let me use Z to denote the random linear combination of the Zi's. Then this random vector Z will have 2/3 non-zero entries in expectation. Why is that? Because every row, if it's all zero, then it's already zero, like after any linear combination. If it has one, then it will be perturbed into 0 or 1 or -1 with equal probability. So in expectation, this is true. So we can de-randomize it, and we also don't want the trivial linear combination. How do we de-randomize it? Well, you can just brute force, right? K is log n, and the 3 to the log n is poly n. But you can also do something clever like conditional expectation, but you can de-randomize. And
this is where you need K to be around log n, right?
yes, yes. So this means you can brute force of the coefficients and to find one explicit one, such that it has at most roughly 2/3 non-zero entries. And this is because when I set K to be log n, this 1 minus 3 to the minus K will be negligible. Well, will be close to 1. That I don't worry about. Yeah. Also, this is not all zero, like the trivial linear combination. So, okay, now I have this Z, and I'm going to produce minus Z using the first n vectors. How am I going to do this? I just add them together. Like I read Z, and there are 2/3 of the entries are non-zero, and I use the standard basis to produce all those entries, right? And I use only 2/3 of them because there are just the sparsity of Z. And then I combine these two because my goal is to find linear dependence. And I have minus Z, I have Z, I add them together, it's 0. So how many total vectors I use? From here, I use 2/3. From here, I use K of them at most. And K is log n. So in total, I use roughly 2/3 vectors. Okay, even though I started with n plus log n vectors, I only use 2/3 among them. Okay. Does this make sense?
What if the V1 through Vn have a dependence?
Oh yeah, so the actual algorithm you run will be like, you start with n vectors, you find a subset of maximal linear independent set, and then you run this thing. Yeah. But everything is efficient.
But like if I didn't care about efficiency, like couldn't I set K to be much larger? I mean, does that help?
You mean K much, you set K much larger so that your T is much smaller?
Yeah.
Yeah, that's the second slide, the next slide.
Okay.
Yeah, that's the open problem.
Okay. All right. I'll wait to ask more questions.
Okay, yeah. So at this point, I already presented you the algorithm we designed for the F3 subset sum. And let me like pause a little bit here to say about open problems relevant to this problem. And I think it's already interesting. So what I showed you is if you have n squared over 3 vectors, you can efficiently find a subset sum that sums to 0. And the question is, can you improve this n squared over 3? Can you make it much smaller? And well, as I mentioned, 2n plus 1 will guarantee a solution. So information theoretically, you can do it to linear, but we don't know how to do. And even in the random case. So what I presented doesn't assume randomness at all. Like VIs can be arbitrary worst case inputs. And all of our algorithms are like subroutines are deterministic. So, but maybe if you want, you can use random vectors to improve something, but we don't know how to leverage that benefit. Okay. And one way to improve this is to get even sparser reducible vector. So what I showed you is given roughly n vectors in like a F3 to the n, we can efficiently find linear dependence that use only 2/3 of them, right? So like if you can improve this 2/3, you will be able to improve this 1/3, right? You see the how it works. And unfortunately, this is not possible, at least in this parameter setting, because you can like reverse engineer from the proof. Assume the first n vectors are standard basis, and the rest of them are like some vectors, and I can choose. And if you pick random vectors in the rest of them, then with high probability using concentration, all linear combination of them will have like a non-zero entries, like 2/3. And this means if you have like a 1 plus little n little 1 n vectors, you cannot improve this 2/3. Okay. But on the other hand, if we just want to improve that, say, we can use more vectors, right? We have near quadratic of them. We don't have to use like 1 plus little 1. So now let's say if you have like n to the 1.99 many vectors, can you improve this 2/3? And now information theoretically, you can improve it to n over log n. This is by the subset sum argument. Like once you have n to the 1.99 vectors, you compute all the subsets of size like n over log n, and then you will find a collision which produce you a linear dependence. So information theoretically, you can do this, but we don't know how to get it algorithmically. Okay. And moreover, this problem seems to be interesting on its own. So let me give you more. Like not like 1.99, I give you n to the 100. Can you get better than 2/3? I don't know. Of course, solving this problem doesn't improve this subset sum problem, but we also don't know how to do it. And moreover, like for this problem, why stick to F3? Like this seems hard also in F2, right? So let me give you 100, like n to the 100 vectors in binary fields. And my goal is to find a linear dependence of only half, like much smaller than half of them. Like why half? This is the same randomization trick. Like every, like a random vector will have a half non-zero coefficients over F2. So my question is how to beat a half.
This is like L1 6 or something.
Yes, yes, yes. So, right, so you can still do the counting argument, and the limit is also n over log n, but we don't know how to get that. So these are the relevant open problems on this subset sum problem, and I find it very interesting. And you can view it in terms of like maybe coding theoretical way, like you want to find a short code word that has like much smaller than n over 2. And I don't know how to do that. Okay. Okay, so that was the subset sum algorithm. And let me go to this SIS infinite problem. So here I'm having like m vectors input, and I want to produce linear dependence where the number, like the coefficients are bounded within plus minus h, where h is the weight. So if h is p over 2, this is trivial because you just view the field as minus p over 2 to p over 2. And every linear coefficient can be expressed in terms of this range. So this is simple. So this is a simple fact. And the next thing is this weight reduction. And let me start with weight halving. So assume for R vectors, you can get weight to be b, some number. Then I will show you with R square vector, you can halve it. Okay, like here, if you get weight to be 100, with quadratic more vectors, I will be able to produce you a solution that is at most 50. And then let's revisit the result of Imre and Ivanias. They show that assume k is a power of 2, and well, this is where you see a power of 2 coming, and m is sufficiently large. There is a classical polynomial term that goes to h being like p over 2k. And actually, using this lemma, you can shave the p dependence. Like It's like you don't need that. And how do we do this? Well, you do induction, right? K is a power of 2, then it's 2 to the I. For I equals 0, then H is P over 2, and this is the claim. Okay, so this is our base case. And then for general K, you use n plus 1 to the K many vectors, and then to further divide 2, you need quadratic more. So it's n plus 1 to the 2K, and you go from P to the 2K to P to the 4K. So this is just using the weight halving. This is how you reprove their results with a better dependence. Okay. So here, like the previous trick about exploring dimension reduction and sparsity also applies, but I'm not going into the detail of that. You can try to play with the numbers and it will work. Okay, so let me focus on this lemma about weight halving. How do you get better? How do you bootstrap your algorithm? So the way we'll do it, it will largely follow the subset sum algorithm. It will have 3 steps. The first one is to partition the quadratic many vectors into like parts. So it will be R batches of R vectors, and each batch we will run our algorithm in some way. And then for each batch, we will compute some kind of reducible vector. And finally, we will combine those reducible vector in some way so that after expanding it, after substitution, it will have smaller weights. Like it will use smaller like coefficients. And here, the definition of reducible vector changes. So a vector is reducible is if for any integer c from minus b to b, c times u is a linear combination of the vectors using coefficients that are only b over 2. So the range of c is not the whole field, and we want to reduce the weight. And then from this, you will see like how to finish the algorithm, right? If I have all this reducible vector from each batch, then we can just use the starting algorithm to find a linear dependence using coefficients in B, and then use the definition of reducibility to reduce it to B over 2. Okay, so this is how you ignoring the second step, this is how you finish the algorithm. Does this make sense? Okay. Oh yeah, replace them. So the problem is how to construct this reducible vector.
Oh, what was the last line?
Oh, like you replace those with
Yeah.
reducibility. Yes. Okay. So the problem now is to how to construct this reducible vector. And it will also be similar to the subset sum algorithm. So we will, for the ice batch, there are R of them. And what we can do is we use our algorithm to compute some non-trivial linear dependence. In particular, all the linear dependence coefficient will be bounded within B. Okay, this is where we use our assumption. And then we will group those coefficients into buckets. For each S, I will put the vectors that has like plus S and minus S coefficients on it. So yeah, so TS is going to sum over all the vectors with coefficient S and all the negative vector with the coefficient negative S. Why I can glue plus and minus together, this is because in the SIS infinite problem, I don't care about plus and minus. That's why I can do this. And then I will have this vector sum where each TS is sign the subset sum, and I have B of them. Okay, now where is my reducible vector? The reducible vector will be taking the second half of T. Okay, I'm going to sum over T B over 2, B over 2 plus 1 up to TB. This is a signed subset sum. And I'm going to prove to you like why this is a reducible vector by the definition. So first, if the coefficient C is at most b over 2, then this C times UI is already using coefficients smaller than b over 2. This is because C itself is small, and this reducible vector has coefficients in plus minus ones. Okay, so this range is okay. And now, what if C is large? Like C is at least b over 2, but at most b. What we will do is we will subtract this 0. Okay. And then we check what's the coefficients now. So for small s, the coefficient is minus s, which is good. For large s, the coefficients will be c minus s, where c is large and s is also large. And when you subtract them, it's small. Okay. This is because s is small and c minus s is small. And each ti is coefficient plus minus 1. So this is why this CI are constructed is reducible. And of course, you can do it for negative C's, so it's fine. So this means UI is reducible. Okay, so this is how we construct a reducible vector. And in the previous slide, we use reducible vector to achieve this weighted reduction. Everything good? Okay, so in this definition, I didn't mention like a technical subtlety that what if these are all empty? I want to produce something, not an empty sum. So we need to handle this edge case. So what if all these things are empty? Then we go back to the linear dependence we come up with, like using V1 up to VR. It turns out this is empty if and only if all the coefficients are small. Right? And then you can blow up the coefficient by 2 and then recurse. And then you will get reducible vector. So if all the coefficients are small, you multiply them by some constant, and then some of them will be large, like within this range. And then this won't be an empty sum. And then what I said will be okay. Okay, so this is the technical subtlety, just in case you wonder. Yeah. Okay. So this is a weight halving statement with quadratically more vectors. We can halve the weight by 2. And you can do iterative halving, like you can run this many times. So for 2 to the t, the cost of 2 to the t, then you can divide the 2 to the t. This is where they get the power of 2 assumption. But maybe you wonder, like, what about dividing 3? If I just want to go from b to b over 3, and if I use this iterative halving, I will do it twice. So I will pay like r to the 4 vectors and not getting b over 3, but much better, like b over 4. But I don't want to pay this r to the 4 divided 3. So how do we do this? And it turns out we can do this. This is weight trisecting, and once I show you this, it will be kind of clear how to generalize to divide arbitrary number. Okay, so we will pay cubic cost to divide 3. This is as you expect. So what we will do is to follow the same roadmap. We will divide r cube vectors into batch, and each batch now will have r square vectors. And then we will compute reducible vector from each batch and combine them in the end and substitute them into weight b over 3. And now the definition of reducible vector will be different. Like previously, it will be b over 2, and now it will be b over 3. But still, the linear combination will be from minus b to b. And this is how you like finish the proof once we get this reducible vector. Okay, cool. So the focus is still how do we construct this reducible vector? And now I have R square many vectors to begin with. So what we will do is to do the similar thing, like we assumed with R vectors, we can get weight B. So let's take out R of them, even though I have R square of them. So we will take R of them and then compute some linear dependence with weights at most B, and then we will similarly combine them in terms of the weights, like minus S and S. So this is what we get. But different from the weight halving case, we now need to do something like, of course, there are like R square, we need to do something different. So we will partition them into 3 parts. So previously it was 2 parts. And now it's like small coefficients, medium coefficients, and a large coefficient, depending on where the S is. So crucially, each TS is a disjoint sign subset sum of the first R vectors. So I have R square vectors, but I'm only doing things so far on the first R of them. And I group them into like coefficient types. And I will tuple them to be more explicit. So this is going to be converted into a longer vector, which I call X. And the first part will be the sum of T's of the small coefficients. And the middle part is middle coefficient, and the large part is the second part is the large coefficient. And this X, yes, so the small, medium, and the large. And this X is a longer vector that has 3n dimension, because I have like 3 parts, and each one is a vector. Okay. And we can expand it in terms of plus minus v's, and I only use R of them. Okay. And then if we combine them, like combine the v's after the expansion with proper small coefficients, medium coefficient, and a large coefficient, I will get 0. These are all hiding, hidden under the rock, but if you expand it and assign coefficients properly, you will get all 0 straight. And the way to assign the coefficients will be, for the small part, I give small coefficients. For the middle part, I give medium part, I give medium coefficients. For the large part, I give large coefficients. They will have different coefficients within them, but those are all small, or medium, or large. Okay, so this is just like the observation regarding this vector X. And then, okay, this is just a simpler way to write it. X is like a longer vector, and it has 3 parts: small, medium, and large parts. And then we can do this for all batches. So I have R square vectors, and what I described is just using the first R of them. So why don't you do the same for the rest of them? So for each R, we will have some longer vector xi. And we can compute the linear dependence of this X. Right? So this X will be like new factors we constructed based on our input vector. And we use the non-trivial algorithm to begin with to combine them in terms of the coefficients. Okay. And yeah, so this is how we get the linear combination of those X. And for example, okay, this is a concrete example. Like these are the coefficients. So 1 of x1 and the x2 will have coefficients minus b over 4. The fourth one will have b over 2, and the last one will have 5b over 6, and all the rest coefficients are 0. And this is a concrete example. Let's say this is what we get. So the first part will be the first 2 vectors, which have small coefficients. And the second part is median, and the last one is large. And what we will do is to unpack each xi, like each x. So we will get a matrix. And this is a little bit ugly, but it's necessary. So the matrix will have 3 rows corresponding to the x, because x is like 3 vector coupled together as rows. So the matrix will have 3 rows, and the matrix will have 3 columns. This is based on this new linear dependence. You have small, medium, and large. And how do you combine them? Well, you put the correct sign on it. So I will use like this big M matrix to denote this abstract matrix. It's 3 by 3, and it has like these entries, and each entry corresponds to an entry over there. And there are several observations. The first observation is every entry of M is a disjoint subset sum of the original vector R square vectors. Why is this? This is because those combinations are like adding them together up to signs. And each one of them is a disjoint thing of the original matrix or input vectors. So if you unpack into the very beginning, they are disjoint sign subset sum. And every row of them will sum to 0 if you properly give them small and medium and large weights. And why is that? This is like, for example, the first row, like A, B, and T. Well, I use T because I use C over there. So why is that? This is because we obtained a linear combination of X that uses these kind of coefficients. And X is a stacked matrix, a stacked vector of small, medium, and large parts. And this A, B, and T happens to occupy all the small ones. So this vector sum being 0, meaning that like each individual one is 0. So we get the same linear equation holds for the small part, which is the first row. Okay. Okay, so this is what we get. And how do we get like A, B, and T? Like what's the correspondence between this one and the A, B, and T? Well, A is just this x small 1 minus x small 2. So this is A. And this x4 will go to B, and x7 will go to C. Or go to T. And the coefficients happens to be small and medium and large. And because we know it's 0, you sum them together, it will be 0. This is an informal argument that intuitively tells you like why every row is a 0 sum. And also every column is a 0 sum with proper weights. And why is that? For the first column, we know that it's a combination of x1 and x2. And x1 is 0 sum up to proper weights of small, medium, and large over large. And same for x2. And the first column, A, B, and G, is just a linear combination of these two, right? So the first row goes to A, and the second row goes to D, and the last one goes to G. So A, D, and G will also be a 0 sum if you give it proper weight. So this is the benefit of viewing it in the matrix. Like every row will be a 0 sum, and every column will be a 0 sum. Okay, so this is observation.
I don't understand. Can you go back? So the first entry, right, you know that you need to put like the correct weight on x1 small, x1.
Yes, you need to unpack it.
But then x2 small's weight may be different. And I see that because you have the other thing, you can like kind of take a combination of them with 2 small weights and produce another small weight.
So
you got to do that for the medium.
Oh, so the point is like every xi, like all this, like there are six entries, right? Every entry is a sign subset sum that are disjoint.
Yes.
Okay, you will need to unpack all those sign subset sum and give proper weights for every individual one in it. There will be different coefficients for each individual one. So you will give some small one, maybe like 1, 2, 3 here. That's a small. Maybe you will give like 5, 6, 7 over there. That's small. I'm just saying after you unpack everything,
D is like x1 median minus x2 median, right?
yes,
So like if you wanted to put like one median coefficient on x1 and the other, a different one on x2, how do you?
so median is defined to be like the absolute value being median. So it's b over 3 to 2b over 3. So I'm ignoring the signs. So it may be like a minus sign or plus sign.
Yeah,
And
one will have like a different, one will have like, I don't know, b over 3, maybe the other one's.
yeah. So those are all individual ones. Like I don't want them to cancel. Like they don't cancel. I'm just describing like a way to get zero vector. I'm not saying this. I want it to be like I want them to cancel each other. They can't cancel each other because they are disjoint. Like they can't cancel.
I don't know if I'm following, but it's okay.
Yeah. So far, I'm just constructing this matrix M, and I haven't tell you like what is the reducible vector in the end I construct. I'm just doing some kind of preparation work right now. Yeah. So intuitively, what you can think of it is we have a matrix M, and every entry is like subset sum of input vectors. And for every row, it will be equal to 0 after you put corresponding sums, like a coefficient on it. And every column, it will also be 0 after you put corresponding coefficient on it. So this is an intuitive way to understand this matrix. Yeah, so this is every row and every column. So what we have done is to come up with this matrix, symbolic matrix, and we divide the coefficients from 0 to b into 3 buckets, small and medium and large. And then this matrix will produce 0 if you properly, like for every row, if you properly assign them with small and medium and large weights. And also for every column, if you properly assign them like small, medium, and large weights. So this is what I have done right now. And I haven't told you like where is my reducible vector. Okay. So here is my reducible vector. Okay. I'm gonna take this coordinate minus this coordinate. Okay, so I've prepared a matrix for you. And what is my reducible vector? It will be the combination of 2 entries of the matrix. And I will prove why this is reducible based on like these properties. Okay, and now like in the proof, it will have cancellation that you want. So let's go over the proof. Like for the small c, so okay, the proof will be like for every c, it needs to be able to expand into linear sum of b over 3. So for small c, this is already good because I said every entry is like every coefficient of this, every entry of the matrix is a sign subset sum. So if you multiply by c, the coefficient will be plus minus c, so it's small. The non-trivial thing happens for the medium and large case, which is similar in the dividing 2 case. So for the median case, I expanded c times u is c times f minus c times h. This is the definition. And now I need to subtract something so that I get cancellation. Because c itself is big. It's like median. It's not big, it's median. And I don't want that. So what I'm going to do to cancel f, I'm going to use the third column. Why I use the third column? Because c is median and f appears here as median, if you see the row. So I will subtract some small times t, median times f, and large times I. And why I can subtract it is because with this proper coefficients, they sum to 0. So it's a 0. And for h, how do I cancel it? Well, I'm going to use the rows. And I'm going to plus, like add this small g, median h, and large I. And it will also be 0 because this is how we construct the matrix. And then, like these are the like 5 entries of the matrix that are involved. So we need to care about go over all the coefficients. So the coefficient of T is minus small, which is small, and the G is small, which is good. And the coefficient on F is C times median, C minus median, and the coefficient of H is median minus C, and the coefficient on I is large minus large. Okay, this equality is just going from here, and you rearrange the terms. But what you see is these are all coefficients within plus minus B over 3. Well, small is B over 3, and for this part, median is within this B over 3 interval, and C is also in this B over 3 interval. So when you subtract them, they become small. And similarly for here, the large ones, and large is this interval of B over 3, and you subtract them, it's B over 3. So everything is B over 3. Okay, so this is how you get median. And then for the large ones, it's similar. So, but I will use different columns and different rows. Because now F is weighted by C, which is large, and H is also large. So I'm going to use the second column and the second row to produce the desired sum. So if you do this, it will be small, and the median minus median, and large minus large. So everything is still within B over 3. So this is how you get, how you verify all the C's and also the absolute value of them. So this means U is reducible. So the work will be, you do a bunch of crazy things to get this matrix where you can intuitively view them as classified by rows and columns based on the coefficient weight. And then you carefully combine them so that you get a reducible vector.
The main thing you wanted to avoid was subtracting small from large or something like that.
Yes,
Right?
you want
That's the
to,
whole-
yeah. So the reason why you come up with this matrix is you want the same class stay in the same class. And when you have 3 classes, you need a matrix. So in the dividing 2 case, we don't have to do this. Right? It's much simpler, this one is more complicated. Okay, so there are still some technical issue, like if I construct this matrix, what if F and H are empty? And this turns out to be much harder to resolve than this divide 2 case. Recall in divide 2, I was saying, oh, this has very simple structure, and then you can dilate every coefficient by 2, and then you recurse. But here, it's a complicated matrix that we cannot control easily. So what we will do is you need to change a little bit on the algorithmic side to guarantee they are not empty. It's not saying, okay, I'm doing some black box thing and I will be able to guarantee you. It's you need to go back to the base algorithm and to do something slightly different there.
But just to summarize, this whole hard work the last 15 minutes was to avoid when you want to divide by 3 instead of 2. You
Yes.
don't want to go to m to the 4th,
Yes.
but only to m cubed.
Yes.
If you didn't care about this constant.
Oh yeah, if you don't care about this constant, then you don't need that. Yes. Yeah. Okay, so yeah, so in general, you can divide K. And the K over 2 case, you only need R vectors. I already showed you. And this part will be the reducible vector. You divide them into first B over 2 and the last B over 2, and then you take the last B over 2 to be your reducible vector. So this is a pictorial explanation. And for K equals 3, you will start with a column, which is small, medium, and large. And then you need to do it, you need to expand it into a matrix. And then in this matrix, you will single out this 2 entry and use this entry to minus this entry to get your reducible vector. And this requires quadratic vectors to get reducible. And in general, well, okay, so if I didn't show you, but you can imagine if you want to divide 4 without going into dividing 2 and dividing 2, but prove it directly, you will start with an algorithm for K equals 3 to get a matrix. And then
you will like combine this matrix into a cube. So you go one dimension higher. And all the red stuff, I promise you, minus the green stuff will be your reducible vector. And in general, okay, yeah, and this is like going from small to large, but you have 4 paths. And in general, for general K, you will have a K minus 1 dimensional array, because you always go one dimension higher, and you will need to use R to the K minus 1 vectors. And how do you assign this red and green, and you combine them properly to get reducible vector? This will be the permutohedron inside this K minus 1 dimensional array. It's totally not obvious to see, but that's the construction. And as Avi said, if you don't care about the constant, like if I divide 3, I just do like dividing 2 and dividing 2. Like I get 7, I divide 2 3 times, then you don't have to do this work. So this only matters when you want to get the right dependence of n to the k to divide k. Okay. So in general, okay, I have 5 minutes. That should be good. So in the general case, the weight reduction is actually not more complicated. Okay, that was already the most complicated thing in the presentation. But I still, let me just show you. So this was a slide from the previous dividing 3 case. And what we did was to construct the U to be like an F minus H, and we proved it to be reducible. And the way we prove it is to separate for every C being small and medium and large. How do we get coefficients smaller than B over 3? And this is a proof for like B over, like for the large C. And the crucial part is all the coefficients lie within the group. Like for small ones, it's plus minus small. For medium ones, it's medium minus medium. For large ones, it's large minus large. And that's how they are all at most B over 3. So equivalently, I could write this whole explanation without using this like dividing 3, but like from B to minus B. I could use like range of small, medium, and large, and rewrite this reducible vector. This is equivalent. So what it does reducible mean is means for every coefficient C that lies in like small union medium, union large, I want to reduce it into coefficients using like just small ones and medium minus medium ones and large minus large ones. And it happens to be these two things are the same as plus minus small. So this is an equivalent way of viewing the previous like weight dividing 3 proof. And if I write in this way, like why do I have to work with small, medium, and large, right? I can just use abstract set of coefficients, right? Which is H0, H1, and H2. So everything I described works in this abstract way. You don't need to do like check the numerical comparison between them. So you will get a matrix of H0, H1, H2 as rows and columns. And then when you verify it, it will have coefficients within these 3 sets. So this, new coefficients, the reducible vectors, will come up with that proof. So it's like reverse engineer from the proof to the definition. And now this means if you have R vectors and you can do this A allowed set to be plus minus H0, H1, H2, what you can do is to use R square vectors to come up with some reducible vector with this definition. And what you can do is to later combine these vectors so that your new allowed set becomes this set of coefficients.
Do you still want H2 minus H2 to Y and plus minus H0?
No, you don't have to. You don't have to. Like I just put them like, oh, like if it lies in H0, then it's better, right?
Yeah.
So, but in general, you don't have to. So this is the generalization of the previous dividing 3.
But somehow you cannot divide by 3.
What do you mean?
I don't know why, I mean, these sets are now arbitrary, it's not, there's no reason.
They're not gonna have the same
Yeah, I
property.
mean, the sizes don't.
So this is more like in your algorithm design, you do something like I choose to partition A
Yeah,
into this
yeah,
part,
yeah, okay.
and then my new A will be that.
Yeah.
And then with some choice, it will be better. With some choice, it might be worse. And this is like a free for you to choose.
Yeah,
So
but
in-
for random A, you will probably have
Right.
how much
Right.
harder time
Sure.
partitioning.
Yeah.
That's just, you have to be careful how you choose the H0,
Yes.
H1, H2, so they're different, they're pairwise different.
yeah, like towards your
Yeah,
final
you
goal.
cannot,
Yeah.
in general, you cannot.
Yeah,
I mean,
yeah.
they will not be small. anyway.
Right.
Well, you still can, but it will be like not as great saving as dividing 3.
You will only subtract.
Yes.
Yeah.
I will give an example. So this, in some sense, is still dividing 3. It's like dividing this whole set into 3 arbitrary sets and do some stuff. And in general, you can divide K, right? So this is why I showed you. If you have your allowed set, you can in your algorithm decompose it into some H0 up to HK. And after you fix this, you also fix the definition of reducible vector, and you get a new algorithm with new allowed set of coefficients. And it's up to your choice to choose them. Okay. And the base case is still the whole set of allowed vectors. This is the base case. Like, where do I begin with? And this is where I begin with. And yes, so this is what I said. You can partition the base to get generated in your choice. And here, let me show you one example that's like maybe this is one way you can do, but you can do other stuff as well. So for example, for p equals 11, and the whole set is from 0 to plus minus 5, so you have 11 elements. And then I will choose to divide it into 3 parts, where H0 is 0 and 3, 4, 5, and H1 is 1, and H2 is 2. So those are singleton set. Okay. What I'm gonna have is the new A will be plus minus H0, H1 minus H1, and H2 minus H2. But they happen to be 0 for H1 minus H1 and H2 minus H2. So what I get is A equals H1. Oh, sorry, A equals plus minus H0. So this is what you like. You can use this example to show that once you have cubic number of samples, you can use them to combine to get a linear dependence where the only coefficients are using 0 or plus minus 3, plus minus 4, plus minus 5. You can do other stuff as well.
But in general, you will have all the HI, not zero HI.
In the very worst case, yes. In the very worst,
When you save only an additive case.
that's why we only save additive. Yes. Yeah, but in some case, if the allowed set is large, then you can find a arithmetic progression in it. And this is like dividing 3. So we can zoom into those arithmetic progression and you can divide. And that is how you get larger saving. But in general, if you just want to remove some shattered like singleton, then this is the best you can do using this trick. Yeah.
So is this fundamentally restricted to symmetric A?
So what I presented works for the worst case. So if A is not symmetric, you can do you can apply a reduction to shift it. So A to A plus T, like a additive shift. And this additive shift will allow you to go from symmetric to asymmetric. But this additive shift will only work in the average case.
Okay.
Yeah, so this, like, yeah, what I presented will be restricted to symmetric A, but it's worst case.
So you have worst case symmetric A and average case for randoming.
Yes, yeah. Okay, So just a summary. So we give classical algorithms that match or improve previous quantum algorithm. And this is for problems related to short integer solution, especially this tree. And our work shows that there is no quantum speedup for these problems at this moment. But it's possible to come up with like a better quantum algorithm, and we hope to see. And we do not break any crypto assumptions using our algorithm. And also there are other quantum speedup candidates that are similar to the quantum algorithm for these ones that are based on Gibbs reduction. And it's a very interesting question to try to understand the logic or the reason behind them, whether they exhibit different hardness. Okay, thank you.
Question. I have one.
Yeah.
So for some cryptographic assumptions, you can kind of like take attacks and create like a generic model where you're able to do the attack in, and then in fact most attacks will work in a generic model. Is there like some sort of like black box generic model where your attack works in? Does the question make sense? Like,
oh, you want to like abstract the attacks that we designed, and
yeah.
Maybe so. Well, one way to view it is maybe you have, yeah, like solving linear system with like coefficients, bounded coefficients, and if you want to do such things, then you can use our results to have some trade-off. For certain parameter regime, you can solve it. Does this fit in your like fit as what
what I'm asking is a little different, but I can ask you later.
Okay, yeah.
Do you have any natural class of algorithms that maybe you can argue your algorithms are optimal? I mean, the parameters you achieve, like n over 2 to the k. Maybe you cannot improve them in some class of algorithms. I mean, you use very restricted natural type of arguments in the analysis. Is there some barrier kind of
So
result to this class?
yeah, so I think it's natural to maybe prove the optimality of the algorithm in other models, maybe in like space bounded algorithms or like communication setting. But if not in those settings, I think it will be pretty hard to.
No, so I'm fine with somewhat restricted setting, but in which your algorithms fit. So your algorithms, I don't know if they are small space, and I don't know if
the algorithm uses. Yeah, okay.
it's in algebra, yeah.
Yeah, it is it's a bit complicated to analyze the space use, or yeah, I don't know. And actually, I think the algorithm can be improved further. It's not like n to the k should be the correct thing. I think maybe you can. Okay, my personal opinion on this problem is I think you can do it to n square over log n. Yeah, my feeling is you can improve this low order term, but whether like n to the 1.5 or something is possible, that I'm less clear. But I think n square over 2 should be doable. Also, n square over log n should be doable. So I'm not sure whether like our algorithm for this are the optimal ones. So.
Well, any natural algorithm class for which you can prove some law.
Yeah, I'm not familiar
the problems
with.
Peter presented, natural, I don't know, some squares or.
Oh, that's a good question.
Yeah, but here it's the nature of the algorithm is different.
Yeah. That would be very interesting. Yeah, if you can say, oh, n to the k is necessary for worst case choice of allow set A, that will be very efficient.
More questions?
I guess you spend a lot of time thinking about these problems. Have you become more or less confident based on how you think about it? You know, based on what you've thought about, have you become more or less confident in the crypto assumptions?
Oh, well, I think linear number of factors is really,
We're safe. You think we're safe?
I don't know. Well, so for the, well, as I said, I think this n square over log n should be okay. If your hardness is based on like n square over log n, then I don't think it's secure. But that is actually linear, which is close to this TFMP threshold. And there are some variants of SIS problem that are proved to be some PPP complete or some stuff. So maybe those are still safe. Yeah, there are some TFMP results for variants of it, but I'm not the expert on those. Yeah, so I would say I still hope those are secure. Yeah. And I certainly have no idea how to do anything for linear number of vectors.
I have a general question about this parallel wars, nuclear, I don't know, arms race in cryptography and in quantum advantage. In cryptography, people wanted, it was a long-term goal to get obfuscation for a very good reason, because an extremely powerful cryptographic primitive. So you would like to have it and implement it under good assumptions. Here, people are looking for quantum advantage. It's another worthy goal, but not of the same caliber. So people have many ideas, you know, and the question is, are you going to try to refute each of them and invest a lot of time in this or this?
I think,
how worthy is this time investment in comparison to that?
yeah, so there are indeed like proposals for like quantum speed up candidates, and not all of them are natural and interesting problems in mathematically. And well, this is why I spend a lot of time motivating like the problems we study. Like we think these problems are interesting, not like they are natural, but artifact. And there are certainly a lot of work there. I think currently we are lack of like a quantum speed up candidates. So exploring different problems, maybe the settings are a bit strange, is still helpful. Yeah, but you are right. There are several problems that are less natural to study, and it's like to demonstrate quantum advantage, and we design some problem that is weird and can't break it.
Factoring is still a candidate.
Yes, factoring, yes, yeah.
More questions? All right, great, thanks.